One way scientists identify minerals is with color. Now, you'd think color wouldn't be such a hard thing to identify in a mineral. I mean, if it looks purple, it looks purple. But there are several things that can alter a mineral's color. You can have tiny amounts of other elements inside the mineral that may make a brown mineral look purple. It may have contact with air or with water that may make a brown mineral look purple. And you just might actually have some defects in the crystals which might affect color as well. So how do you find a mineral's true color? Well, you have one of these. This is called a streak plate, and it's actually just a white porcelain plate. And what you do, you scrape the mineral across the white porcelain plate, and the true color will show up. And if you can see on this picture, you have brown, which is showing up, but the rock is kind of a greenish brown. The mineral's kind of greenish brown, so that shows the true color. And that's one way scientists identify minerals. Another way they identify minerals is something called luster. If you look at the pictures we have here, the silver is really shiny, and scientists would call that a metallic. And you can see I got the another mineral down below called anatase, which is, well, it's not shiny at all. So you can see that scientists categorize that one as non-metallic. So luster can be broken down into metallic minerals and non-metallic minerals. Another way scientists categorize minerals is how it breaks. If a mineral has, well, the two terms that go with this are cleavage and fracture. If a mineral has cleavage, it will break along flat surfaces, kind of like tiny little rectangles and tiny little squares. But if it does not have that, it would have fracture. If a mineral breaks and it has fracture, it just breaks into little jagged, irregular pieces. And that's another way scientists can categorize these minerals. Fourth way scientists can categorize minerals is with its density. Now, density is how heavy something is. You've probably heard this analogy before. You have a baseball and a tennis ball, and they're about the same size, but a baseball is considerably more heavier than a tennis ball because it has more density. Now, the example we can use with minerals is, for example, gold and pyrite look the same. They both have the same metallic luster, but gold is 4 times as dense, and that's one way it can be separated from pyrite. A fifth way scientists can identify minerals is with their hardness, and scientists have developed a scale called Mohs scale, M-O-H' scale. It's used to describe the mineral's hardness, and you can see on the screen it says from 1 to 10. 1 would be talc, 10 would be diamond. Diamond is the hardest mineral that we know of, and talc is incredibly soft. Now, if you take for example, a mineral that is a 7 and scrape it against a mineral that is a 6. Quartz is a 7 and feldspar is a 6. If you scrape quartz and feldspar together, which one would have the scrape on it? It'd be the one that's the smaller number. The feldspar would have the scrape on it. Quartz would scrape feldspar. There's one way you can take two minerals that are next to each other and find out which is the hardest, the one that would make the scrape on the other one. Now, fortunately, we figured out that a fingernail is about a 2.5 on Mohs scale. So if you scrape a mineral with your fingernail, it's 2.5 or less if it leaves a scratch. Copper penny is 3 to 3.5, and a knife blade would be 5.5. So all those that are higher than 5.5 on Mohs scale could not be cut by a knife. You know, there are some other things that can identify minerals as well. We've mentioned 5 of them, but there are 3 others that the book are going to make casual reference to.
You can see what they are: fluorescence, the ability for it to give off light, magnetization. Believe it or not, there are some minerals that are magnetized. They are naturally magnets. And radioactivity. There are a few minerals that give off radioactivity.
And we already talked a little bit about mineral classifications. You know, you may remember that silicates are the most common classifications of minerals. I have here some pictures of some silicates, carbonates, and of oxides. Silicates happen to be here. Silicates, you may or may not remember, come from two of the most common elements that you find in the Earth's surface. It's silicon and oxygen. Isn't it ironic that oxygen, known for being a gas, is present in many, many different kinds of solids? Well, anyway, about silicates, they're the most common, and I think over here we have feldspar, which we've mentioned before, olivine, muscovite. Not quite so much on silicates, as we'll talk about some of the others, some of the ones that's least common. Carbonates is one that we happen to have mentioned. Here's pictures of carbonates. In fact, it's the same carbonate. It is calcite. Now, one thing I want to point out about this picture, we have calcite, same element here, same mineral here. However, it looks so different. We have some piece of calcite that looks kind of greenish, a piece of calcite that looks very white. Minerals can get slight impurities to them that really change the color a lot. In fact, even here you see some kind of streak of something, some kind of impurity that happens to be in there. May even be a different kind of mineral in there. Other things to know about calcite: chalk, even though is not a mineral, comes from carbonates. Calcite is common in seashells, and one common way to figure out if something is a carbonate is to take hydrochloric acid. I'm going to abbreviate it into its chemical name. Hydrochloric acid dripped on carbonates will bubble. The acid reacts and forms a carbon dioxide gas, which is the bubbles. So that's a little bit about carbonates. Let's talk now about oxides. Whereas silicon and oxygen make up silicate, and carbon and oxygen, I'll abbreviate, carbon and oxygen make up carbonates, oxygen is also part of oxides. However, in oxides, an oxygen is paired with some kind of other element that is usually a metal. And as a result, we end up having many metals that can be formed from these oxides: tin, copper, and even this particular metal here, or this particular mineral here called hematite, is a mineral that helps form iron. Okay, kind of shifting gears here. Your book mentions several ways to identify a mineral: streak, color, luster, hardness using Mohs scale, all things such as that. There happen to be some other ways that I want to kind of briefly mention. We have this mineral here, which is called fluorite. Some minerals glow when exposed to ultraviolet light, and fluorite is one of them. It's called its fluorescence. And fluorescence is a little bit unpredictable. Some samples of the same mineral will reflect more, and some may even not appear to reflect at all. So that's not a steady and true way to test for what a mineral is. This next one is called magnetite. And if you haven't noticed already, it appears to be magnetic. A few minerals respond to magnets, and it makes it easy to separate these materials from the ones that aren't. There are also a few minerals that are radioactive. This one right over here, tellurium, is radioactive. It gives off energy, actually. Minerals are necessary for our modern way of life. Some of the minerals that are, some of the ways that is the case is in our cars we have metal. In our airplanes we have metal that comes from minerals. We mentioned in some classes about making glass. In modern glass making, you have minerals that kind of help with the modern glass making. In common products such as toothpaste, you actually have minerals. In paint, we have minerals. And in our photographs, there are compounds in photographic film which have minerals. And of course, probably the most common is going to be jewelry, or at least that's what minerals are known for. their jewelry. You could find gold and silver and diamonds and rubies and all kinds of jewelry, probably even in this building. Uh, but when these jewels are found in nature, they're not near as polished as they are whenever they're shown off. They're very rough and irregular. But you, of course, have people who are good at polishing and cutting out these stones and precious metals to where they really look good.